We are live. Hello, ast111x. I'm Frank Timmies.
I'm Brent Smith.
And we're the only ones here right now. So hopefully Jackie and Becky will join us soon. So the way we'll start out is I will talk a little bit about the final, and then Brent's going to take some of the questions that were posted on our Google thread. Then I might do a little presentation on calendars and times. And then we'll play it by ear and see if Becky and Jackie come on or if anybody has any other questions. You can post questions on the Google thread, or if you want, you can post questions. There's a little chat window you should be seeing. You can go ahead and chat, type your questions in there, and we'll see how we can answer them. Okay, the final is coming up next week. I believe you've got all next week to do it. For those taking it for credit, it is proctored. It's closed book for everyone. So it's much like Quiz 2. You can kind of think of Quiz 2 as a practice session for the final. The final is comprehensive. It covers all of the material in the course. The questions are at a level that is commensurate with what you saw in the homeworks and the labs, although perhaps a little easier than what you saw in the labs. Questions I would ask in a lab, I would not necessarily ask in a final. There are approximately 50 questions. You have 3 hours to do that. Can I think of anything else? Do good on it. Do well. Can boost your grade up a whole grade point if you do well on it. So it's not particularly hard. Just study the material. Go over your best study guide is the homework and the quizzes. Go over that material and make sure you can answer those. And if you have any questions on those, certainly ask on the discussion board. I'll be happy to answer them, and we'll go from there. Okay, Brent, why don't you take a couple of questions that are on the have been asked?
Sure. So I think, let's see, there was a question about the significance of gravitational wave observations. Yeah, that one seemed most interesting to me. And so because I actually took GR, and so I got to study how it actually works out mathematically, which is actually very interesting. And in the class, they told us that gravitational waves are purely theoretical, and they've never been observed directly. But Einstein theorized that they did exist. And so really the significance of this LIGO detection is that it proved that theory was correct. And we can actually theorize about things that we haven't observed mathematically and actually look for them and actually detect them in reality, which is really why that's so significant, I think, because we can actually imagine things that haven't been even observed yet and think of them and then look for them and then see them in real life. So I think that's why that's so special. And this was a purely mathematical thing before it was ever observed. So that's why it's such a great discovery to me. And
I'll tag on to that.
Yeah, do you have thoughts on that?
Yeah, sure. It's kind of like opening up a new window for us to observe the universe. It was kind of like maybe the first time people started using radio waves to explore the universe. And so this opens up a whole domain that we've been blind to before now. And I think over the history of astronomy, it's been shown over and over again that once you open up a new domain of observation, that you discover all kinds of cool new things about the universe. This LIGO detection is not the first. I think they have several in the can
Yeah, yeah,
that are going to be waiting to come out.
yeah,
And so this is just sort of the first ones on, we'll be opening a new domain in astronomy. So it's kind of cool.
yeah. That's another good thing, and they can see these objects that could never have been observed through current methods, like with CCDs and other like photon counting devices. You can see black holes merging now. Like you're saying, it opens this new domain and things that were completely invisible. So that's another very neat thing about this. Even like, um, despite like this scientific like achievement, just like this new technique shown to work, like it's pretty awesome itself.
Right. Cool.
Um,
Let's see. You want to take any of the others?
yeah, and then another one that I can probably talk about is it was KJ Heifkins. He posted about the flat radial velocity profiles of the galaxy. I think the Milky Way. About the discovery. So what I know, from my understanding, it's there were some astronomers that looked at the velocities of stars in the Andromeda galaxy, and they saw that the further out in radius the star is, the velocity doesn't really change that much. When you start getting out in like the spiral arms and out past this central bulge, where stars are pretty kind of randomly, um, their velocities are randomly dispersed. And so they can, well, according to the theory, there was, it didn't follow the typical Keplerian pattern like the solar system. So they had to like somehow figure out what this, why this effect is occurring, basically. And it was either that the theory of relativity was incorrect, or there's some missing matter that's making these velocity profiles so constant, even though there's no observable matter there that would explain this velocity gradient. And so that's basically why dark matter is theorized to exist. It's this effect of the radial profiles of the velocity. And although it's never been observed directly yet, even though there are experiments out there looking for dark matter, like some like dark matter annihilation, or like an interaction with xenon, which I'm not exactly sure how it works, but somehow the xenon can emit light when it interacts with dark matter, and they can observe that. So, but which hasn't happened yet, I guess. So that's
Definitely hasn't happened yet.
yeah,
That would be pretty big. That would almost be as big as gravitational waves, or
probably yeah.
or an Earth's twin in another solar system.
That's true. So we would know about that.
Right. I'll pick up one of them. Just sort of science at work. This one was from Lori. She is smart. Looks like this the acronym there of the name. Yeah, and about, I guess, God, when was that? About a year ago. Maybe a year and a half ago, there was a story that came out that suggested that bacteria, basically that you could base life off of arsenic. That you had bacteria that could eat arsenic, and therefore arsenic was a viable energy source for life.
This is carbon life forms?
Yeah, arsenic-based
Oh, arsenic based. Okay.
Arsenic, consuming arsenic based, and hence arsenic based life. Um, that story created a lot of buzz when it first came out, and sort of as a lesson in the process of science, it didn't last very long. There were apparently problems with the technique that was done in the lab and control samples in the lab. And like any science, it has to be reproducible by other people. You want to see things twice. And other people could not replicate that experiment, or had troubles with the way the experiment was done. And so basically that claim has been discredited, I think is a fair way to say that. Some of the protagonists might argue otherwise. But yeah, it certainly got a lot of heat. And it kind of goes to the, the claim that if you have an extraordinary claim, you better have extraordinary evidence to back it up. And life forming on arsenic is an extraordinary claim, and it just did not hold up to scrutiny over time. So maybe it'll come back, right?
I hope so. That sounds cool.
It would come back, but the experiments, I think, would have to be a lot better. So that's a little bit of science at work. Lots of claims sometimes, and not all of them pan out. It's kind of the bloody, messy edge of science.
Are there other systems out there besides carbon-based life forms? Do you know of?
People have talked about silicon. People have talked about germanium. I think there was even a Star Trek episode where life was based out of silicon. So people have talked about it, and in principle, you can do it. It's right underneath carbon in the periodic table, so it forms bonds just as easily. Silicon and gallium are not as abundant as carbon, nitrogen, oxygen. Right? There's a reason life as we know it is made out of the most abundant metals, or most abundant heavy isotopes elements that there are. So it's been theorized, but certainly nobody's produced anything in the lab. But people have just raised it as a possibility that that if you're going to go searching for life, you can't immediately throw away that hypothesis that it could be silicon based. In fact, if you look in the periodic table, anything underneath carbon is fair game.
So carbon is like an optimal molecule it makes like the optimal molecules for life to exist.
Yeah, because carbon has four open slots in its outer valence electron. It's filled with 4, so it's half full. So it can either take electrons or it can share electrons. And so it's quite versatile. It can go one way or the other. And because of that ability to either take or give electrons in molecules, you can form very long chains with it. And that's the key to carbon. That's why carbon is chosen as opposed to life being made out of nitrogen or oxygen, which are not as flexible in their outer valence electron orbital.
So it's very effective at exchanging charge and energy, really.
Exactly.
And so maybe silicon is just a lesser efficient molecule or atom for that kind of transport.
Right, and there's just less of it by abundance in, for example, the sun or anywhere else. So, but it's not out of the realm that you could do it, or nature could do it, unless you're making a Frankenstein or something. Okay, let's see. Why don't we shift gears a little bit? I'm going to try a little presentation. You can call it the ast111x missing lecture. On time and where some of our notions of time come from. So let me see if I can, you're going to have to help me here, Brent. Tell me if you can see the screen share. Let's try this one. Start screen share. Can you see it?
Yep.
Great. Okay. I'm going to talk a little bit about time. And as usual for my modules, there's an opening quote. This one from John Steinbeck. In the short reign of Pippin IV, who was a story about a commoner who suddenly found himself king. And he had one hobby, and that was astronomy. And so one of the lines in the book is, the passions of astronomy are no less profound because they are not noisy, contrasting astronomy with the political process. And maybe you can compare that to the current political process in the US if you like. So this is just a nice little piece of art here. Interlude, Time Through the Ages. Let's see if I get my buttons going. Okay. So 'tis the season. So if you're an agricultural-based society, it's absolutely critical to know what the season is, know what the time are, because you need to know when to plant and when to expect the first frost. And so this is why astronomy was a survival tool early in human history. However, as societies grow more complex, they want to start having fixed dates for things like your birthday, or the 4th of July, or an Independence Day, or paying your taxes, whatever it is. Society wants to have, the same date every year for certain things. And this immediately introduces a problem of keeping time with what the sun says the time is, the seasonal time, and what humans want to say the calendar time is. And this odyssey, these errors have been played out over the last couple thousand years, and we're going to talk a little bit about some of those. So this is the essential problem. The time we say what the calendar says, and the time in the season what the sun says. Okay. So just for reference as we go along, the seasonal year is defined as going from vernal equinox to vernal equinox. That's the spring equinox to the spring equinox. And it is at about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. So 365 and a little less than a quarter of a day. And just a wonderful painting there by Salvador Dali on persistence of memory and the bending of clocks and how we're going to bend clocks to make the sun sort of bend toward our will. Okay. So yearly calendars were often based, the earliest calendars that humans had were often based on summer solstice to summer solstice, or when a particular star first rose with the sun. And when a star rises with the sun, that's known as helical rising. And the image here is an example in the year 2000 BC. This is July 15th in Alexandria, Egypt. And you can see the sun there. The sun is on the green track there, which of course is the ecliptic. That's why Mercury, Venus, and Uranus are all along the ecliptic. And Sirius has just risen before the sun. Sirius shown there in the image, just above the horizon in Canis Major. And so the Egyptians used Sirius, which also happens to be the brightest star in the sky, and it rose in early July. In fact, it rose at 5:40 a.m. 2000 BC, when the Nile was in flood. And because the economy, the finance, the money was based on the Nile floods, the helical rising of Sirius was therefore the most important, and therefore first day of the year, because that was the money day. So the first of the year was actually in July for many parts of one of the dominant cultures at the time, the Egyptians. Sirius, as we mentioned, is the brightest star in Canis Major. It's sometimes called the dog star. That's what Canis Major means. And it's from the Egyptians' use of the helical rising of Sirius in early July is where the phrase comes, in the dog days of summer. If you've ever used that phrase or heard that phrase and you wonder what the heck that meant, that's because Sirius is in the constellation Canis Major, the dog, and it would rise in the summer in July, and hence the dog days of summer. There's a nice picture of the sky from Uranographia, Johann Hevelius. Okay, so what's a month? So now that people have decided what the year is, we're going to go summer solstice to summer solstice, or the rising of a particular star, Sirius. How do you then divide up time within a year? Well, the most obvious thing to use is the moon. In fact, that's the root word of month, moon, month. But there are two main obstacles with using the moon to subdivide a year. And there's a lunar calendar that the Aztecs used. So the Aztecs had a lunar-based calendar, and that's the Aztec calendar stone there, which is on display in Mexico City. So the first obstacle to using the moon is that the lunar month varies between about 29 and 30 days. It's not the same. And this variance of 29 to 30 days is due to use what's called the synodic period rather than the sidereal period. Now, the synodic period is the time between identical sun, earth, and object alignments. For example, full moon to full moon. The synodic period is easily observable. You observe it every month, full moon to full moon, new moon to new moon, quarter moon to quarter moon. But it's not very useful because it varies around a little bit. The sidereal period, that's the true period. This is the real period. This is the time between an identical star, Earth, and object alignments. This is the period that you would stick in Kepler's third law, or that you would stick in Newton's rendition of Kepler's third law. It's harder to observe. It doesn't go full moon to full moon. What did I just say? Let's check that out. So here's the scenario. We have the sun. We have the Earth there in blue, orbiting the sun in this approximation. And then we have the moon in purple orbiting the Earth. And then we have a distant star. And so in this illustration here, we've got everybody lined up. The sun, the Earth, the moon, and the distant star. It is a full moon alignment. And we have a moon-star alignment with the Earth. Okay, so this is going to be our scenario, and now we're going to let time roll on. So time will roll on, and at some point, in fact exactly 27.322 days later, you will have the same alignment between the moon, the Earth, and the distant star. This is the sidereal period. This is the real period, okay? The one you put in Kepler's law. But notice that the moon is not full at this point. In fact, it's in one of the quarter phases. So the moon has to travel a little bit longer to get back to the full moon position. Why? Well, because the Earth has moved along in its orbit. And so it takes a little bit more time to reach the full moon again. And this is the time, this is the synodic period, full moon to full moon. And it's variable, 29 to 30 days. Okay, so there's something new in this class, the difference between a synodic period, easy to observe, not so very useful, and the sidereal period, harder to observe, but the real deal. The second obstacle is that the year can't easily be divided sort of by the average lunar month of 29 and a half. 12 lunar months is 11 days too short, and 13 lunar months is about 19 days too long. And so as we'll see this scenario played out over and over again, such a lunar calendar is slowly going to get out of step with the seasons. So that if you kept that calendar, eventually the hottest time of the year would occur during what we call the winter months. And again, this is all due to the time that the sun says it is and the times that we want to keep. And so many cultures, Aztecs included, got around this conflict of 29.5 not being divisible into the year by inserting an extra 13th month every few years. And this was all done to keep the seasonal and calendar years synced. Okay. Other fun things about the moon. So it was common practice in Babylon about 4,000 years ago that for a month after the wedding, a whole month, the bride's father would supply his son-in-law with all the mead he could drink. So mead is a honey beer. And since their calendar, the Babylonian calendar was lunar-based, or the time within a year was lunar-based, this period after the wedding was called the honeymoon, or the honey month. And it's where we get the term honeymoon from. So that term honeymoon is as old as the Babylonians. Other terms that are associated with the moon are the lunatic, right? Luna, lunatic. We got blue moon. Where does that come from? We have things like wet moons, harvest moons. And so all these terminologies that we use still today in everyday life have their root in using the moon as a time marker for within years. So the Egyptians eventually gave up on using the moon to mark time within a year, and they took a more radical approach than the Babylonians or any other culture before them. They are the ones that divided the year into 12 months of 30 days each. 12 times 30 gives you 360 days. And at the end of every year, they added 5 days for an approximation of 365 days. Now, they knew that 365 was not the exact period of the Earth around the sun. And so extra days were randomly added to keep the seasonal and calendar years synchronized. So it's all the way back to the Egyptians of where we get this 12 from, right? 12 months, 30 days. That's the origin of sort of the baseline of the calendar. And again, the Egyptians used Sirius, July, the heliacal rising of Sirius, to mark the first of the year. Then along come the Romans, and the Romans had a surprisingly messy calendar. The year was 10 months long. Like I said, it was messy. And in the Roman world, March was the first month of the calendar year. And extra days were inserted at random to keep the seasonal and calendar years together, and that sort of varied by locale within the Roman Empire. And just to put this in modern terms, so we get this from the Romans, so September, October, November, December. These were the 7th, 8th, 9th, and 10 months in the Roman calendar. And so the name of our months come from the Romans, although it's not 7, 8, 9, 10 anymore. It's 9, 10, 11, 12. But September, October, November, December from the Romans in their messy calendar. And it was so messy, in fact, that somebody decided to do something about it. And so Julius Caesar, about a year before he met Brutus there, and he had his famous death there, he instituted a new calendar across the Roman Empire. There would be 12 almost equal months. March would still be the first of the year, the opening of the new year, totaling 365 days. Except, rather than randomly putting in, now every 4th year or leap year, an extra day was added at the end of the year. So that would be at the end of February. And this gave an average of 365.25 days. And so it's from Julius Caesar is where we get the idea of having a leap year every 4 years. So 365.25 is a better approximation to the year. And of course, it's very regular now because we're going to add time every 4 years. So this is a more uniform clock rate. Now, Julius Caesar liked his new, more accurate calendar so much that he decided to name a month after himself. And this is where July comes from. July is for Julius Caesar. Political power loves money, and money loves political power. And in Julius's time, there was a very wealthy and powerful family that was aligned with Julius, and their last name was the Junos. And so Julius also decided to honor his money benefactors, the Junos, with a name of a new month. And so this is where we get June from. So June and July are from Julius Caesar and his wealthy benefactors. Of course, now the pattern was set, and every Roman emperor past Julius had to take a new month for himself. The first one stuck. August comes from Augustus Caesar. And fortunately, all the ones after that who decided to rename months for themselves did not stick. But June, July, August, that's an ode to Julius and Augustus Caesar and their benefactors. So 365.25 is close, but the Julian calendar, as it's known, is about 11 minutes too long. You know, you kind of live with that. So it's only off by 1 day in 130 years, or after about a week in 1,000 years. And okay, who cares about that? We'll worry about that when we get there. And in fact, we got there. So by 1582, because we were using the Julian calendar, the seasonal and calendar years were about 10 days out of sync. And so Pope Gregory decided to do something about this because this was getting ridiculous. Summer was slowly sinking into winter if we kept this going. So it is he, in 1582, who introduced the Gregorian calendar. Now take a careful look at this calendar that I've got printed out here in October of 1582. And what do you notice? Notice that it goes October 1, 2, 3, 4, 15. So he chopped 10 days out of the calendar immediately in order to get things back into sync. And this created near social chaos, right? Well, does this mean I don't get paid? Do I have to pay taxes? Just all kinds of social unrest on near riots almost on chopping out 10 days out of the calendar. But nevertheless, he did it. And so we got back on track. And now he implements basically the system we have today. So Roman was rather pagan. And so Pope Gregory of the Catholic Church just is the one who makes January 1st the beginning of the year. So this is where it comes from. And every 4 years, an extra day is added to February. We have one this year. We have February 29th this year. And so he is the one who then implements a little bit fancier rules of century years are divisible by 400 are leap years. And so 1700, 1800, 1900 aren't leap years, but 1620 are leap years. And so this is a little bit more accurate than Julius Caesar's calendar. In fact, it's only 38 seconds too short, or about 1 day in 2200 years. So what are we going to do? Are we going to wait another 2200 years until we're out of sync again and go through this game one more time? No, enough is enough. And so now in the modern year, we have 1 second added to the calendar clock at midnight on June 30th or December 31st, when the difference between what our clocks say and what the sun says, the seasonal and calendar year clock, reaches 1 second. And the calendar clock, i.e. the time we want, uniform time, is maintained in Paris using a worldwide system of atomic clocks. And the seasonal clock, what the sun says it's doing, is based on observations of Earth's rotation, and that is done by the U.S. Naval Observatory, and that's where the image is there, the International Earth Rotation Service. So they're the ones who keep track of how the Earth is spinning around and moving in its orbits. This one you already know. Why are there 7 days in a week? Because there were 7 objects that moved in the night sky: the sun, the moon, Mercury, Venus, Mars, Jupiter, Saturn. So went all the way back to the Romans doing that, Babylonians doing that. But our names come from the Norse Celtic barbarians, and we kind of covered this in the first week of the course. One thing I bet we didn't cover is, where do time zones come from? Where'd that come from? Who invented that? So before time zones, every clock was set properly according to their local astronomical conditions, right? So noon in Phoenix, Arizona was not noon in Yuma, Arizona, which is all okay until people decide they want to travel. And so some of the first major travel systems were trains. And so not having a time zone created major confusion as to when times were scheduled to arrive or depart. So if you said noon, did that mean noon in Phoenix or noon in Yuma? And what was the difference in time between Yuma and Arizona and Yuma and Phoenix? And that was all too much. So it was the railroads in 1883 that introduced schedules that standardized entire regions across having a single time for the purposes of railroads. But it was such a groovy and great idea that in 1918, the U.S. Congress made the rail zones official in the U.S. under federal law. And then in about 10 years later, 15 years later, the international bodies at the time made it across the globe. Of course, all those zones are subject to political influence, and so none of them are particularly completely straight all the way through. They bend around to political realities and country realities and cultural realities. So there's sort of a time zone map, and you can see the time zones sort of bend around according to desire and whim. And that's what I wanted to say about time, where it comes from. How we doing? We can anybody else? No, no, Jackie, no, Becky. Okay. Let's see.
So is there an integer number of moon cycles as there are solar cycles, the sidereal?
By solar cycles, you mean like the sunspot cycle?
The sidereal cycle.
Mm-hmm.
Is there like an integer number of each that like overlap?
There's probably a close pair of integers. I don't think it's an exact integer match.
Because you said that there was 29 to 30 days for each moon cycle.
Right. So you're asking, is the sidereal, the 27.3, does that exactly fit in 265?
Or some number of years?
Yeah. And in fact, I believe that was the basis of the Aztecs choosing a lunar calendar. So yeah, if you wait enough years, you will get an integer match between the number of times it goes around on average on a synodic and the year. So yeah, I believe this was the basis of the Aztec calendar. And amazingly enough, the Aztecs pushed their calendar out thousands of years more than what their current time was. And so every couple of years this comes up. And I think the official sort of Mayan or Aztec calendars sort of end like on that stone we saw. This, I believe they ended in like 2015 or something, which is 1,000 years more than where they were. And so, then there's the usual, well, this will be the end of the earth, and, the end of the world is coming because the Mayan calendar ran out. And
I remember.
Yeah, sure. So that one comes up every once in a while, right? Another destruction of the earth because the Mayan calendar ended. Okay. Yeah. But yeah, you're right. And probably other cultures may have had that as well, but the Aztec and the Mayans are the ones I'm most familiar with there.
Is it like hundreds of years or like 1,000 years? Do you know?
I don't recall
around
the integer match. I suppose if we took 365 and 0.2422 and divided it by 27.233, that would give us a real number, and then we'd multiply by whatever.
Yeah.
Move the decimal point until you got something that was close to an integer.
Yeah.
Until you got a zero somewhere in that string, right? And then that would be close enough to an integer. So I don't know what that division is, but we could do that. But yeah, it was something along those lines. And I don't remember whether it was hundreds or thousands or what that nearest integer would be, but easy enough to figure out.
Yeah, that's true.
Hey, that's a question we could ask Astronomy 111x to figure out on the discussion board. Now you know what the next homework question is, people.
Preview.
Okay. Let's refresh my discussion board, see if anybody's added any new questions. Google Hangout topics. No, I don't see one. Well, if Jackie was on, Jackie was going to talk about mistakes in, well, let's call them oopsies. Oopsies in the astronomy and some relatively recent science fiction movies. But she's not on, so she's not going to be able to do that. That's a bummer. Got a question about terraforming. Maybe that was possible given our current technology. I gave a link to a pretty long article from Universe Today. About as complete an article I've seen on terraforming in quite a while. But at the end of the day, no, we don't have the technical nearly the technical skills in order to do that. We just don't have it. Number two, it takes a tremendous amount of resources to change a planet. And number three, it's a slow process. Unlike some movies where the whole planet gets a complete makeover inside of a few movie seconds, and it all looks so wonderful and beautiful. It won't be stable if you do that. You can't change something that quickly and expect it just to hang out. So it's a slower process than people might imagine. But anyway, it's a pretty interesting article on terraforming if you want to check that out.
Do you think we'll have the technology sometime soon in the future?
That's where our art tells us we're going.
Yeah.
Science has always sort of taken to some degree, science has always sort of taken its cues, its leads from what our art, what our imagination, what our desires guide us to. We got the Dick Tracy watches. Remember, Dick Tracy would fly around in a sort of like pod-looking thing, and he had this watch, right? Or he could print stuff, and he could talk to people. It was like this all-purpose watch, and we basically almost got that now, right? With these smart watches that people got. I mean, the Dick Tracy watches are here. Why? Because that idea of how cool would that be to have that wearable device, going back to Dick Tracy. Other examples are stuff that we got out of like Star Trek, right? Cloaking devices, right? The Klingon cloaking device. That's a very active field in physics of, it's not called, well, in some cases it is called cloaking, but how do you make stuff invisible, particularly at certain wavelengths? So if you wanted to make something invisible in radar or in radio waves or in visible light, how do you do that? And that's led to some remarkable advances in material science on exotic types of materials, things that have negative indexes of refraction and stuff like that. And of course, the transporter idea is always a good one. Right? Pick up all my molecules and move it over here very quickly. So yeah, I think in general, it's so that guidepost that we take from our art and our science is a driver. Terraforming, wow, I don't even know if I want to begin to guess the time scale for that, but it's certainly, it's all I can say, it's something that our art points us to doing. And at some point, if we, when we have to leave Mother Earth and we have to go somewhere, yeah, we're going to have to do something. What that is, I don't know. It might be terraforming. It could be something else, but assuming we last that long.
Yeah, unfortunately, it's inevitable. We'll have to leave.
There was a Russian rocketeer, and I forget exactly what the statement was, but it was, you don't have to remain in the cradle forever. In other words, if you want to grow up, you've got to get out there and do it.
Yeah.
So maybe there's a good reason it takes a while to get there.
The sun. Well, we have at least till the sun turns into a red giant, which is in like 8 billion years. So
5. Sun's about halfway through its life right now.
Okay, so then I think we have time.
We've got some time, especially on our time scales. 100 years is about what we last, round numbers. So yeah, 5 billion years is a lot of generations. So hopefully we get smarter and stop fighting with each other. Yeah. Okay, that went off the beaten track a little bit. Let's see. Anything else? I don't want to talk about one of these. Yeah. Okay. Well, I think unless there's something you want to talk about, we can end at. We've been on about 45 minutes here. We can end a little bit early if you like, or if you've got something you want to go on, we can do that.
Yeah, I'm just kind of sad that Jackie couldn't talk about oopsies and science fiction movies. But
maybe what we can do is have her just record a session. That's
a good idea.
She can do her own Google Hangout all by herself, or or she could have we could do a third Google session, and maybe she, you know, at her convenience, we could do that. So she could either post a YouTube kind of video on her topic of oopsies in movies, or we could do a third Google Hangout and it'll just be Jackie.
Yeah.
That's a good idea. Yeah.
Because I wanted to like kind of add in to, well, kind of discuss those with her. Just I thought it would be interesting, but yeah, we can save that till maybe the next one.
Yeah, some of the movies she mentioned, she wanted to do Gravity. She hadn't seen Interstellar yet, so she needs to see that one.
Oh, she has to see that. That's
Interstellar is cool. Another example of our art pushing where we had. Yeah, and I forget what the other two movies were, but she was interested in it. But yeah, we'll talk to her and see if she's interested in doing it. Okay.
all right.
Otherwise, I'm good.
Yeah.
Okay. Brent, thank you very much for showing up at this Google Hangout, and everyone, thank you for either joining in live or watching this Hangout recorded. And we'll see you on the discussion boards, and possibly, if Jackie's willing, we'll do a third one on astronomy and movies. Okay.
Thanks.
Bye-bye.
Bye.